Hello everyone, welcome back to this online class. My name is Francis Okech and my YouTube channel is Professor Francis Okech. So today we are going to look at Calculus 2 and our main topic is on applications of definite integrals, and in particular we are going to look at areas of surfaces of revolution. So first of all, we need to know what we mean by a surface of revolution. And this simply means that it is the surface formed, it is the surface, yes, let me use the word generated, surface generated when, or simply generated by rotating a curve about a line. That line is what we are calling the axis. It can't be x-axis, y-axis, or any other line. So when you rotate a curve about an axis, you are going to generate a surface. And that surface is what you are calling the surface of revolution. So we want to see how to find the area of such surfaces, the surface area. So we are going to consider two cases of the axis. The first one is when we rotate about the x-axis, and another one when we rotate about the y-axis. And remember, you will also rotate about any other axis. So you write case one. Case one is rotation about the x-axis. Rotation about the x-axis. So let's consider the graph of the function y is equals to f of x between x is equals to a and x is equals to b. We need to rotate that graph about the x-axis. So let me sketch it so that I don't write so many things. I have the y-axis, the x-axis. Now this is our curve. Let's say we have something like this. That we need to rotate. So this is y is equals to f of x. Between x is equals to a, this is a, and this other point is b. That is b. So when you rotate it, you are going to get something like a surface, which we need to find its area. So when you rotate, you're going to get this kind of a curve. Of course, I'm going to extend this and also this point so that we'll have something like this. And you see here, it will now be like circular because we are generating a surface. So this is a circular. Even this other side is circular. So which kind of a shape is this one? It looks almost like a cylinder. Almost like a cylinder, though the cross-section area are not the same. The area at point A is not the same as the area at point B, but it's almost like a cylinder. So that is when you rotate about the x-axis. So this is the axis of rotation. Axis of rotation. So we need to know how to find the area. Look at here, the distance from A to the curve is y because it keeps changing. This distance is y, or is the radius. Which is, in this case, it is y. It keeps changing, even here to here, it's still the radius. So how do we find the area of that surface that is generated? Remember how to find the curved surface area of a cylinder. I want us to take note. Take note that the curved surface area of a cylinder is equals to 2 pi r h, where r is the radius of the base and h is the height of the cylinder. Now, in this case, this is almost a cylinder, yes, but now the radius keeps on changing. That's why you see those the top and the bottom, or the areas of the cross section are not the same because the radius keeps on changing. And the h here, what we are calling h, if you look at this line here, if I extend it, a straight line, you see, and then this one, we are going to form something like a triangle where the distance from here to here is approximated by dl. So here it is dl, here it is dx, and here it is changing y. So it means dl is now the height. So therefore, the area of this surface, the area for the surface area, let me look, right, surface area, surface area, you relate to that of the cylinder, that will be 2 pi times radius times h. In this case, h is the arc length. Arc length. That's how to find that surface area. Now, do we know the radius? In this case, the radius is y. It keeps changing. So we are going to replace that radius and the arc length by radius is y and the arc length is L or dl, so that our surface area can be written as dA. So, or you can just write or dA to mean a small change in the surface area is equals to 2 pi. Our radius is equals to y. And our arc length is equals to what we are calling the dl. So instead of A, let me use S just from the definition of a surface area to mean surface area. So let me call it ds, not dA. ds is equals to 2 pi y times dl. Now, how do we find S from this formula? And you know how we find the arc length. Take note that dl from our formula previously, we found dl to be not dl but L. dl was equals to the integral from, not the integral, but the square root. That was the square root of 1 plus dy over dx. And this is supposed to be squared dx. That's what we found. So I'm going to replace it there. So this is now equal to, you can just write or or ds is equals to 2 pi y times the square root of 1 plus dy dx squared times dx. So to find s, we now integrate both sides. Integrate both sides. You take note that when you integrate ds, take note that the integral of ds will give you s. So you can just say hence, to get s, remember 2 pi is a constant, you can factor that out. So we are integrating from x is equals to a to b of, instead of y, you could write that f of x, because y is equals to f of x. So we just write y times the square root 1 plus dy over dx squared. Integrate this with respect to x, where y is equals to a function of x. So this is how to find the surface area of a solid of revolution about the x-axis. This is surface of revolution about the x-axis. Area of surface of revolution about the x-axis. So that's the formula. What about if we have revolution about the y-axis? What happens? I'm again going to sketch it. So we write case 2. Case 2. Case 2, you write rotation about, or simply rotation and revolution, just the same. Rotation about the y-axis. If you rotate your curve about the y-axis, what will be the area of the surface generated? So again, let's sketch. Come up with another sketch. We have the y-axis as our axis of revolution. And now we have the x-axis here. So our curve is something like this. But now you see we are rotating about the y-axis. So let's say we have something like this. Such kind of a curve. That is still y is equals to f of x. Y is equals to f of x. So between, we want to rotate it between y is equals to, can we use c and d? We could use c to this other point, y is equals to d. So I'm going to extend so that I get the corresponding image of that curve. It will be something like this. That one. So that here we have something circular. This is circular. Even this side, it is circular. Something like that. Again, you see this one looks like a cylinder where the radius keeps on changing. This is the radius now. The radius of our cylinder. You see this radius is x. It is parallel to the x-axis, so let that radius be x. And this one is ds. And this is dl. So everything, we need to find the surface area. So the area, surface area is equals to, remember the cylinder is 2 pi r h, 2 pi times radius times height is the same as arc length. Arc length. So you can just say, or ds is equals to 2 pi. Now our radius is x, not y. Then arc length is dl, which we know to be, now look at dl in this case. In this case now dl is given by the square root. Now you factor out dy squared. Remember it is dx squared plus dy squared. So when I factor out dy squared, I'm going to get this. It will now be the square root of dx over dy. This is supposed to be squared plus 1. Remember dy squared, when you take outside the square root, it becomes dy. So the square root of that times dy. Because now we are going to integrate with respect to y. So take note of that. So that here we'll talk of 2 pi x, the square root of 1 plus dx over dy squared times dy. So to get s, you integrate both sides. So therefore, s is now the integral from y is equals to c to d. Of course, 2 pi is outside, so let me rub this and write 2 pi is equals to 2 pi, the integral from c to d of x times the square root of 1 plus dx over dy. This is supposed to be squared, then this dy. Integrate that with respect to y. So this is when you revolve it about the y-axis. So this is area of surface of revolution, area of surface of revolution about the y-axis. Sorry. What about if you have any other line, any other axis? What are you supposed to do? Is not the x-axis, it is not the y-axis, but is any other line. Can be a line parallel to x-axis, a line parallel to the y-axis, or an oblique line. So let me sketch another one. You could write case 3. A revolution about x is equals to a, where a is not equal to, let me start with y is equals to a. The line y is equals to a, and in this case, a is not equal to 0. Any other line. So what are you supposed? So in case 3, a case where we have a horizontal line different from the x-axis. So let's have a rough sketch of such kind of a line. So we'll have the y-axis and the x-axis. Let me draw a better line. Y-axis and the x-axis. Let's say our curve is this one. I can come up with a better line. It's something I want to illustrate. Let's say y is here and x is somewhere here. X and this is y. So let's say our curve is something like this. We want to rotate about, our axis of rotation is now this point. This is the point A, or the equation y is equals to A. So now when you rotate, remember, this one you bring it down up to somewhere here. The same to this. So that upon rotation, we are going to get a curve like this, where this is circular and this one is also circular. Now, what is the radius? Let me extend this x-axis. So this I can extend it x-axis. So now look at the radius. The radius is this, the distance from here to here. It keeps on changing. This distance is the radius. Is it still y? No, because up to here, from 0 up to here, it is y. From 0 to that point. Now, what is the distance from y? Well, this is our radius. It is y minus a. That's very important. So our radius is now y minus a. Our height is still dl. So that the area, surface area, our surface area is equals to 2 pi times radius times arc length, which is simply equal to 2 pi. Our radius is y minus a. Our arc length is dl. And this you can write as, remember here it is ds. So 2 pi y minus a. dl is the square root of 1 plus dy over dx squared times dx. That's our dl. So therefore, to get s, so therefore, s is equals to the integral from, let's say, this point and this other point. This point is x naught. This point is x1. So from x is equals to x naught to x1 of 2 pi. 2 pi is a constant. So let me factor that out. So I'll rub this and write here 2 pi s is equals to pi times y minus a times the square root of 1 plus dy over dx. This is squared. Integrate that with respect to x. That is the formula. When a is equals to 0, we go back to the rotation about the x-axis, because x-axis has the equation y is equals to 0. So this applies to case 1 and any other horizontal line. Excuse me. So what about any other vertical line when you're rotating about a vertical line different from the y-axis? So this is a general case of rotation about horizontal lines. This is rotation about horizontal lines. A can be 0, A can be negative, A can be positive. This is the formula. Lastly, let's look at when you rotate about any other vertical line. That will be case 4. So you can write here case 4. A rotation about the line x is equals to b, where b is not equal to 0. Or b could also be equal to 0. That restriction is not even important, because when b is equals to 0, we get the y-axis, which has the equation x is equals to 0. So I'm going to generalize this again. Let's have this axis and this one, y-axis, x-axis, and let's say our curve is this. Our curve is this. Let me draw a better one. Let's say it is something like this. That is something like this one. Yeah. So you could write x is equals to a function of y. We want to rotate it about the line x is equals to b. At this point we have b. So this is x is equals to b. That's our axis of rotation. X is equals to b. Now we are going to extend this. Also this. So that upon rotating, you're going to get a curve like this one, of which this is circular. Even this one is circular. So this is dl. And now look at our radius. This is our radius. This one is the radius. The distance from here to here is our radius. Now, if I let this point to be x, our radius is the distance from b to x, which is x minus b. So that distance is x minus b. And so therefore, surface area is equals to 2 pi times radius times arc length. Now this will be equal to ds is equals to 2 pi. Now our radius is x minus b. Arc length is dl. And so this you can as well write as 2 pi x minus b. And then dl is the square root of 1. Now it is dx over dy. Dx over dy squared. I already explained why. I already explained this in case 2. Then times dy. So if I want to get s, I integrate both sides. So let's say we're integrating from this point to this other point. This is y0 to y1. So you can just see that therefore s is equals to 2 pi is a constant, factor that out. The integral from y is equals to y0 to y1 of x minus b times the square root of 1 plus dx over dy. This is supposed to be squared dy. So that's how to find the surface area when your axis of revolution is a vertical line. And this case 4, when b is equals to 0, it will reduce to case 2. Take note of that. And also case 3, when a is equals to 0, you go back to case 1. So what about a slant line? When you rotate about a slant line, is it possible? You go check on that one. So I want us to look at some examples. And number 1, you are asked to work out this problem. Find the area of the surface obtained by rotating. So the question is, find the area of the surface obtained by rotating. Surface obtained by rotating the arc. Y is equals to the square root of 4 minus x squared about the x-axis. From x is equals to -1 to x is equals to 1. You just need to know the formula. Even if you don't know the formula, it is easy to derive the formula, because look at how I was deriving my formulas. It's very easy as long as you know that whatever shape you're going to get is like a cylinder, and you are finding the curved surface area of that cylinder. So let's answer this question. Rotation about the x-axis, we know the formula to be this, that s is equals to 2 pi, the integral from x is equals to a to b of y times the square root 1 plus dy dx squared dx. It's better to write down the formula so that you know what you need to find. So that's the formula. Now, what do we have? This is our a is 1. Not 1, but -1. We are starting from -1 to 1. So our a is -1. Our b is equals to 1. Our y, where there's y, you are going to write the square root of 4 minus x squared. So let's find dy dx. What will it be equal to? When you differentiate, you're going to get, remember this is the same as 4 minus x squared raised to 1 over 2. So use power rule, differentiate the power, we are going to get 4 minus x squared raised to -1 over 2 times -2x. I'm using direct chain rule. You start by differentiating the power, then times the derivative of 4 minus x squared, which is negative 2x. So this you can write as, remember that these 2 will cancel with this other 2. So it's like we have negative x over the square root of 4 minus x squared. That's what we remain with. Now that is dy dx. We need to square it. So find dy dx squared. So therefore, dy over dx, you square this to get negative x over root 4 minus x squared. This is supposed to be squared, and so that will give us x squared over 4 minus x squared. So now I want 1 plus dy over dx squared. This is the same as 1 plus x squared over 4 minus x squared. Get the LCM. LCM is 4 minus x squared. Here we'll have 4 minus x squared plus x squared. And so this, the x squared will cancel. This and this will cancel. So what we have there is simply 4 over 4 minus x squared. Now we need to get the square root of what we have found. Hence, the square root of 1 plus dy over dx squared is the square root of the answer that we have found, that is root 4 over 4 minus x squared, the square root of everything. And that will give us 2 over root 4 minus x squared. So now lastly we need y times the square root of 1 plus dy over dx squared. What will it be? We said where there is y is the same as the square root of 4 minus x squared. Then times 2 over root 4 minus x squared. Remember, this is y. It was this one here. So this will cancel with this, and the result here will be 2. So this is our integrand. You see the way we have worked it out, we have simplified, so that's the integrand. So instead of this, instead of the whole of this one, let me show how the whole of that, we are going to replace it by the value that we have found here. So you can just say hence that surface area is now equal to 2 pi, the integral from -1 to 1 of 2 dx, because our answer is, we have found 2 as the integrand. And so this is the same as 2 pi. When you integrate, you get 4x, not 4x, that should be 2x, correction. When you integrate, you get 2x from -1 to 1. And so this is 2 pi. When I substitute 1, I'm going to get 2 minus -2. And so that is 2 pi times 4, which is 8 pi. So because surface area as the units of square units, 8 pi square units, that is the area of the surface that is generated when you revolve such kind of a curve about the x-axis. Let me give you another one, where now we need to revolve about the y-axis. So we can write example number 2. This example 2. That was example 1. So in example 2, you are asked to work out this question. You are told that the arc length of the parabola, y is equals to x squared from point 11 to 24, from point 11 to point 24 is rotated about the y-axis, is rotated about the y-axis. Find the area of the resulting surface. Find the area of the surface generated, or the resulting surface. So this is rotation about the y-axis. Look at the formula in case 2. So we start by writing this formula down, that surface area is equals to 2 pi, the integral from y is equals to c to d. This is c, not 0. Can confuse somebody. Let me write c. This is c to d of x times the square root 1 plus, now it is dx over dy. This is supposed to be squared, then dy. So from the formula, it's now easy to know what we need to calculate for. In the equation we are given, look at the y value at 0.11. So c is equals to 1, d is equals to 4, y is equals to x squared. So I need x. This means x is equals to the square root of y. So having found that, we need now to find dx, dy. That should give us, remember root y is the same as y raised to 1 over 2. So that should give us 1 over 2 times y raised to negative 1 over 2, which we can as well write as 1 over 2 root y. I need to square it, so dx over dy squared. That is equals to 1 over 2 root y. And this is supposed to be squared. It's the same as 1 over 4y. So now we add that 1 to the answer. So I need 1 plus dx over dy squared. So we write 1 plus dx over dy squared. That's the same as 1 plus 1 over 4y. LCM is 4y. Here we'll have 4y plus 1. So that's what we have. And now the square root of that one, what will it give us? So now you can write the square root. The square root of 1 plus dx over dy squared. It is simply the square root of 4y plus 1 over 4y, which you can as well write as the square root of 4y plus 1 over the square root of 4y, which is 2 root y. And then lastly, we need x times that square root. Lastly, we need x times the square root of 1 plus dx over dy, and this is supposed to be squared. Look at our x. We said x is the same as root y, so that would be the same as root y times the square root of 4y plus 1 divided by 2 root y. So this will cancel with this one. So it is simply 1 over 2 times the square root of 4y plus 1. So instead of the whole of this one, we are going to replace it by the answer that we have found here. So that's what we now integrate with respect to y to get the surface area or the area of the surface of revolution. So you can just say here that hence that surface area is now equal to 2 pi. The integral from y is equals to 1 to 4 of 1 over 2 times the square root of 4y plus 1 dy. You see, 2 and this other one will cancel. So this is the same as pi outside. This is y is equals to 1 to 4y plus 1 raised to 1 over 2 dy. So the task is, how do you evaluate that integral? So you are going to use the u substitution method. So you're going to say that let u to be equal to 4y plus 1, so that du dx is it? No, it should be du dy, because now we are differentiating with respect to y. So you write du dy, that should be 4. Or dy, if you cross multiply and make dy the subject, you'll get du over 4. That's what you find. You must also know how the limits of integration will change. So when y is equals to 0, well, not 0 but 1, when y is equals to 1, what will be u? If you put y1, u will be 5. And when y is equals to 4, u will be equal to 4 times 4, 16, and so that is 17. So therefore, this integral can now be written as pi times the integral from u is equals to 5 to 17 of u raised to 1 over 2 times du over 4, which is the same as pi over 4. The integral from u is equals to 5 to 17. This is u raised to 1 over 2 du. Now use power rule, add 1 to the power, then divide by the resulting power. So we are going to get pi over 4. This is now u raised to 3 over 2. 1 over 2 plus 1 is 3 over 2. Then divide by 3 over 2 from 5 to 17. How else can you write that? 3 over 2 you can factor out. So pi over 4 divided by 3 over 2 is like pi over 4 times 2 over 3. Pi over 4 times 2 over 3 Then here now we have u raised to 3/2 from 5 to 17. That's what we have. Now you can now plug in the limits of integration. When you start with 17, remember this can as well be written as, if I simplify, even if I plug in the limits, this will go here 1, this will go here twice. So it's like we have pi over 6. This is the same as root u cubed. Root u cubed from 5 to 17. And so when you plug in those limits, you're going to get pi over 6. The first one is root u, which is root 17 cubed, minus root 5 cubed. What is root 17 cubed? It's the same as root 17 squared times root 17. So this is the same as, take note that when you write root 17 cubed, it's the same as 17 times root 17. If you write root 5 cubed, is the same as 5 root 5. So therefore, our surface area will now be pi over 6 times 17 root 17 minus 5, the square root of 5. This is square units. Square units. So that's how to find that area of that surface. And now you see I've looked at case 1 and case 2. When you find time, please try to look at other problems where the axis of rotation is neither the x-axis nor the y-axis, any other horizontal line or any other vertical line. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Oketch. If you go to the YouTube search, type Francis Oketch or Prof. Francis Oketch, and you will find me right there. Also, don't forget to comment, share, and like this video. When we meet next time, we'll look at other applications of definite integrals. Bye-bye.